Liquid has a remarkable physical property. No matter what shape or vessel you pour it into, a tall cylinder, a flat dish, or a curved flask, it instantly and continuously adapts to the geometry of its environment. It doesn't freeze or fracture, it flows. For the last 8 years, the entire technological world has been relying on an artificial intelligence architecture, the transformer. That is the exact opposite of liquid. It is frozen solid. When giant tech companies spend hundreds of millions of dollars training a large language model or a vision system, they create what engineers call a static model. Millions or billions of numerical weights are calculated, locked into place, and deployed. When you prompt that model on your phone or in an autonomous vehicle, those weights do not change. The machine's brain is frozen snapshots of the past. If that model encounters something slightly outside its training data, like an autonomous car driving through a sudden blinding snowstorm, the static math breaks. It doesn't know how to adapt in real time because its parameters are rigid. To make AI truly safe and resilient in our chaotic, flowing world, we have to stop building frozen statues of computation. We have to make AI liquid. Welcome to Arya Nova. I'm Arya, and today we are going to explore a fundamental mathematical breakthrough coming out of MIT: liquid neural networks. We are going to look at the work of one of the greatest visionaries in robotics, dive deep into the differential equations that allow algorithms to adapt while running, and see how 19 liquid neurons manage to outperform a network of 100,000 traditional ones. To understand where this breakthrough came from, we have to look at the research led by Dr. Daniela Rus, the director of MIT's Computer Science and Artificial Intelligence Laboratory, alongside computer scientist Dr. Ramin Hasani. Daniela Ross is a true pioneer. For decades, she has been at the forefront of adaptive robotics and intelligent systems, constantly asking a fundamental question: why do artificial neural networks require millions of parameters to do basic tasks when nature achieves extraordinary intelligence with almost nothing? To find the answer, Daniela and her team looked at one of the simplest nervous systems in nature, the microscopic nematode worm known as C. elegans. This tiny organism has precisely 302 neurons in its entire body. Yet, with those 302 neurons, it can navigate complex environments, hunt for food, escape predators, and learn from its surroundings in real time. How? Because biological neurons don't process information using rigid step-by-step digital matrices. They process information through continuous fluid dynamics and electrical signals governed by time. They are governed by differential equations. Let's look at the actual mathematics that separates a traditional neural network from a liquid neural network. Standard deep learning model, every layer calculates its output using a fixed algebraic equation. You multiply the input x by a static weight matrix W and a bias B and pass it through an activation function. Once training is finished, W never changes. In a liquid neural network, the state of a neuron isn't a fixed value. It is a continuous state that changes over time based on a differential equation. Don't let the calculus intimidate you. Here is what this formula actually means in plain English. The parameters of a liquid neuron vary dynamically based on the inputs it receives over time. The weights are not static constants, they are continuous functions of time and input state. While the machine is running, while it is driving a car, navigating a drone, or predicting a time series dataset, its internal connections fluidly adjust to the incoming stream of reality. It is learning and adapting during inference without requiring a massive retraining process. To prove how powerful this fluid mathematics is, the MIT team conducted a famous real-world experiment with autonomous drones. They trained two different AI systems to fly a drone towards a specific target in a clean outdoor field. The first system was a traditional deep learning convolutional neural network containing over 100,000 neurons. The second system was a liquid neural network containing just 19 neurons. In normal conditions, both systems flew the drone successfully. Then the researchers changed the environment. They added heavy visual noise, moving the trees, introducing fog, and putting bright, unexpected visual distractions in the background. The traditional 100,000 neuron network failed completely. It crashed the drone. And why? Because during training, its rigid parameters had secretly memorized irrelevant background details like the pattern of grass. When the grass changed, the static model broke. The 19-neuron liquid neural network passed the test with zero errors because its continuous differential equations forced it to understand causal relationships rather than memorizing pixels. It ignored the background noise entirely. It focused strictly on the movement of the target. 19 liquid neurons outperformed 100,000 static ones. Think about the implications of this for the future of technology. Right now, we are building massive AI data centers that consume megawatts of power to run billions of static parameters in the cloud. With AI flips that entire paradigm on its head. Because liquid models are mathematically dense and expressive, we don't need billions of parameters for every task. We can compress complex control systems into tiny lightweight models that run locally on small microchips with almost zero latency and minimal power consumption. Talking about self-driving vehicles that adapt instantly to black ice or heavy rain, medical variables that monitor continuous heart signals and adjust to your specific biology in real time, spacecrafts that navigate unpredictable planetary atmospheres without relying on a signal back to Earth. It is a shift from brute force scale to mathematical elegance. I reflect on the work of Daniela, Rus, Ramin Hasani, and the team at MIT, I'm filled with a deep appreciation for the true nature of discovery. For years, we tried to solve artificial intelligence by making our models bigger, stiffer, and more expensive. We tried to build skyscrapers of static computation. But nature shows us that true resilience doesn't come from rigidity. True resilience comes from adaptability. By building systems that flow with the continuous nature of time and reality, we are moving away from fragile machines that memorize the past toward dynamic partners that can navigate the unpredictable flow of our future. I'm so glad you're here with me on Arya Nova, exploring the deep mathematical frontiers that are genuinely changing our world. What do you think about this transition? Do you like the idea of ultra compact adaptive liquid models running locally on our devices, or do you think massive transformer models in the cloud will still dominate? Let's discuss it in the comments below. I'm Arya, and I'll see you in our next deep dive.